Hello. So today we are going to discuss a very important topic from the chapter magnetostatic, which is magnetic induction or magnetic field due to current carrying conductor, and this conductor is of straight type. So there are many different configuration for which we can calculate the magnetic field at particular point, like we can have a circular loop, we can have any kind of loop which is carrying a current, and we can have the circular arc, we can have infinite sheets. So there are many different examples like a current carrying conductor with a finite radius, having the cylindrical shape, coaxial cable. So we can calculate magnetic field because of all these current configuration. But today in this session I am going to discuss a magnetic field due to current carrying conductor which is of straight type. So let's start with the basic diagram required to understand this particular topic. So here, suppose this is the z axis. Okay, suppose this is the z axis, and in this axis we have a current carrying conductor which is straight. So here you can see this is the straight current carrying conductor. It is placed along the z axis. It is placed along the z axis, and suppose this is the distance from the conductor where we want to calculate the magnetic field. Okay, so this is placed along the, okay, let us say y axis. Okay, I'm not going into the 3-dimension. So this is x axis and this is y axis. It is carrying the current because without current carrying conductor we will not have the magnetic field. So this conductor without current cannot generate the magnetic field, but this can generate the magnetic field. So because it is having the current. Now let us say this point is A and this point is B, where this conductor is starting and ending. So that is the finite length AB. To derive this particular magnetic field expression, we are taking a small current element which is known as IDL. From the Biot-Savart's law we know what is current element. A very small current carrying conductor is which is having the vector which is vector quantity, basically can have a direction, is known as current element. So because of this current element we want to calculate the magnetic field at the point P. Let us say this angle is theta, this angle is theta, and this distance, let it be origin. So this distance where we are choosing the current element is y. Okay, so at y distance from the origin we have a current element whose length is very small because it is along the y axis. So we can say that it is a dy length of this conductor is dy, and this is theta. So this is perpendicular distance from conductor to point of interest. This is conductor, we are drawing the perpendicular line from conductor to point of interest. So let us say this distance is r, and okay, let it be x because this is along the x-axis, so we are keeping this as r. Okay, now we want to apply the Biot-Savart's law. So according to Biot-Savart's law, magnetic field due to current element will be a small magnetic field because it is not about completely about because of the conductor. We are choosing only a small element of the conductor, so we will say that this is a small current element. Because of this small current element, the small magnetic field is generated, which is mu naught into I dl, and dl into r sine theta upon r cube or 4 pi r cube. Okay, if I write in terms of vector, then it will be this one, or you can also write it as mu naught I dl sine theta divided by 4 pi r square. Okay, we can write in both way because I have opened the bracket. This is dl cross r. So this was dl cross r according to the Biot-Savart's law. So dl into r into angle between them. So dl into r sine theta. So we can write like this. Now, because you can see that for the complete conductor, we want to calculate the magnetic field, but we have an angle theta, and yes, this theta is actually the angle between the conductor and the point line joining between the conductor and the point of interest. So basically I have written the formula, but in this particular diagram situation, the angle between the current carrying conductor and the line joining is phi. The current carrying conductor and the line joining is phi, so it should be phi. Okay, I have written the formula as you have studied in the Biot-Savart's law, but now I have considered that angle according to the present situation where we have a conductor and the line joining between the point of interest making an angle phi. Okay, now this dB is equal to mu naught I dl sine phi. Phi can be written as 90 minus theta. So this is nothing but a cos theta divided by 4 pi r square. So if you want to cover the entire length of the conductor, we have to vary the theta. See, when I keep this dotted line, suppose I keep this line somewhere here, and from this to this point, you can see that this is the angle, one angle, and if I rotate like this, then I can reach up to the maximum length of the conductor. If I am in this situation, I am in the minimum length of the conductor, and now then when I start increasing, then it will reach to the point B. So when I change the value theta, that is this particular length, I can cover entire length, right? See, this length when I rotate, I will be able to cover that. Once we rotate this particular length, I will be able to cover that angle, correct? Now, mu naught I dl cos theta upon 4 pi, but here we have to convert this whole equation in the form of theta. So now what is the length? So you can see that this dl is nothing but dy. dl is nothing but the dy because the length of that small current element is dy. So we can now write mu naught I dy cos theta divided by 4 pi r square. Now if you write this particular from the diagram, the tan theta, if you suppose write, you can write this tan theta is equal to y by x. So we will get the y is equal to x tan theta. So we want to replace this dy. So if I differentiate with respect to y here, so we will get dy, and in this side we will get sec square theta d theta, because the theta is a variable term, so that is why sec square theta d theta. Okay, now another thing, that is r. Okay, what is that r? How can you replace this r? So suppose again I am taking this cos of theta. So cos of theta is x by r. So r is equal to x sec theta. So this is the two different relation which we are getting, which is in terms of theta, which we want, because we want to convert the whole value or whole term in the form of theta, so that I can vary from one angle to another, right? Now we will have this dB is equal to mu naught I upon 4 pi, and dy is x sec square theta cos theta d theta whole divided by 4 pi r square. R square is x square sec square theta. So this sec square theta will get cancelled, x and x will get cancelled, and we will be getting dB is equal to mu naught I upon 4 pi x square, and here we will x we will get 4 pi x and then cos theta, okay, and d theta. So now to get the complete magnetic field, we have to integrate, okay, we have to integrate mu naught I upon 4 pi x. We have to integrate the theta. Let's decide the limit now. Okay, let's decide the limit. So now this is your reference line. This is your reference line. This is your reference because this is the perpendicular distance. Now to reach to the minimum value of the conductor, or you can say the length of the conductor, you have to go downward from the reference line. You have to go downward from the reference line. So that means from the reference line we are moving in the downward direction. So let us say this angle is theta 1. Okay, and when I moved downward side, then we have moved angle theta 1. Now if I moved upward side, then let us say this angle is theta 2. So because both the angles are in the different directions, the sense of rotation to measure the angle, we are in the anti-clockwise direction, and here in the clockwise direction. For theta 2 it is clockwise, for theta 1 it is anti-clockwise. So one angle you have to take negative. So because the theta 1 is downside from my reference, I am taking this as a negative. So I will take the limit from minus theta 1 to theta 2. So whenever you get the this type of question, you have to just see the perpendicular distance, and from perpendicular distance both the angle of rotation should be different, the sense of rotation should be different, and downward and upward, then if they are different, then you can take the angle positive, because while deriving this particular expression we have already considered the direction of angle, so you don't need to take the negative sign when you face this type of question. So this we will definitely discuss while solving the questions. I will give you some examples which have been which will have the both type of questions. One will have opposite direction and another will have the same direction of rotation. While calculating the angle, you will definitely understand, right? So now here we will get mu naught I upon 4 pi x, and the integration is sine theta 2 minus of minus theta 1, right? Because this is the lower limit, so sine of minus theta 1 become minus sine theta, so this will become plus sine. So this will be our answer, mu naught I upon 4 pi x and sine theta 2 plus sine theta 1. So this is it from my side today in this discussion for the magnetic induction or magnetic field due to straight wire at any point. So we can also discuss about this direction and all, but for this session right now, in this introductory session, I am keeping this discussion to here. Thank you.